Perfect. So exactly, as I said, I'm John Kalkoff, and I'm going to present two of our works. One of the IPNI, where we received the Francois Absorn Prize, and also at MICAI, where we got the Young Scientist Award. So the topic I'm going to present today is on robust and lightweight segmentation with neural cellular automata. And before we start with that, let's have a short look at the access to healthcare worldwide. And a problem that you generally have is that especially in the Southern Hemisphere, you have a lot of countries where there's a general lack of access to healthcare. And this, you can see here in the map, represented by the density of physicians per 10,000 population. So that's a big issue in these cases. And of course, the best case to solve this would be to take the people that are in the country and educate them to become doctors. But that's a lot easier said than done, because you need the according resources. First of all, you will need a lot of time to get enough people to be done with the education. Then also you need the money to actually do so, and also the educational facilities. So that's more like a long-term task. But if you want to solve this a bit more short-term, something that is also maybe a viable option is to introduce some machine learning methods to help the existing physicians in doing their daily work. And particularly if we're going to talk about segmentation, this is also what this talk will be about. We are going to look at UNet type architectures. This is basically the most used architecture in the past 8 years for a lot of good reasons. It works very well on segmentation tasks, but it also has a huge issue, and that is that it requires quite strong hardware. We're talking about millions of parameters, and those we have to have the proper infrastructure. We need a strong GPU, and especially if we're going for high resolution images, it becomes more and more unfeasible where we actually would need this. So what would we actually need to solve such a task? So first of all, we would need a method that's lightweight. So we want to basically run it on any possible hardware. We want it to be possibly scale invariant, so that we can basically apply to any input image that we would receive. And also it should, of course, be robust against different types of domain shifts, as we want to have a method that is also not going to fail just because there is a small shift. And the solution to all of these problems is neural cellular automata, and we're going to see in the next 20 minutes why that is. But let's first shortly talk about the three advantages that I have talked about. First of all, the lightweightness. So if we now compare the UNet type architectures with the Med-NCA, something that you can see immediately is that neural cellular automata are very small. That's due to the one cell model size. We will talk about that in a moment. And they only have 30 to 70,000 parameters. And even our newer method that has been published at MICAI only has around 13,000 parameters. So it's about 2 to 3 magnitudes smaller than existing methods. Also, we have a big advantage in comparison to the UNet type architectures, in that there's no need for cropping or rescaling, because the method is by design able to handle different input sizes. And this is an advantage you would also get with fully convolutional networks. But with the UNet, this is just not possible. So this is one other advantage. And then lastly, also we have the robustness against artifacts, where we're going to show that it also is able to handle these rather well. But before we're going to talk about the NCAs, we should maybe shortly talk about the cellular automata, so where this whole idea is coming from. So the idea behind cellular automata is a bit older. It goes back about 20 to 30 years for most research. And the most well-known example is probably the game of life. And the idea behind the game of life is that you have a set of hand-designed rules. In this case, it's 4, and they only consider the state of a cell, so alive or dead, and the neighboring cells. And based on this, only this information, it will make an update to the cell. And then this rule that we have just designed is iterated multiple times. And as we can see here, iterating this rule multiple times results in this. In this case, we have this initial setup of these kind of like a generator that produces these gliders. And the very interesting part about this setup is that it actually has been proven to be Turing complete. So depending on the input state and the world size, we can basically achieve any computational program. And this just basically shows how powerful such a small rule can be if you apply it over and over again. And in 2019, then this idea has been combined. And the idea was basically to replace the hand-designed rule with a neural network And this way we can actually train it. And this has been done in 2019, the first time, basically replicating the results of the Game of Life. And then in the short years after, there have been a few publications exploring that for more advanced tasks. So here we can see two examples that I was searching out. So first of all, we have the growing NCA example, which basically initializes an image from a single pixel, and then by applying the same rule over and over again, we ultimately arrive at the salamander. And it's actually very robust. They train it to be able to handle different types of perturbations. It's also a very interesting demo if you want to learn more about NCAs. This gives a quite good intuition, so the website is highly recommended. And then also the second example is image generation based on NCAs, which also just shows that with this very little number of parameters, that's actually quite some information that can be stored there. But how does this actually work in the neural network? So first of all, as we said, we have a one cell model size, and we also want to store some information between the steps. So that means that we can think of it as each cell having a feature vector of usually around 16, and the model can store information in between steps there. Then, as we also, of course, want to have some communication with the neighbors, we'll have a convolution as the input to the model, and this way we can learn some information about our neighbors. As we, of course, also want to have some global information, as we want to do a segmentation task, we also iterate this rule multiple times, and iterating it multiple times then allows us to gather this global information we need to perform the segmentation. And the way this works is if you iterate it n times, you're getting a perceptive range of n each cell, which is it's very logical if you think about it. If you run it 0 times, you only have the information that's stored in that cell. If you run it once, you get information about the neighbors, and since these also communicate with their neighbors, it just increases by 1 with each step. So if we're looking at it in this way, we basically have a 3x3 convolution. This information is then passed to a neural network in a very simplified example here, and then we add it to the previous state as the cell update. But the problem is, if we actually want to do a high-resolution segmentation task, we are running in a few problems. So first of all, we have very high video RAM requirements. That's because while the model is very small to actually train it, we have to keep all the duplications of that rule across the whole image space. So already in 2D, if we're having like a 300 by 300 image, we would talk about 20 to 40 gigabytes of video RAM for just a single batch size. And also across time, because we are running it for a set number of steps. And afterwards, we're expecting the segmentation. So this is a big issue. Then, in addition, the training is also difficult because since we have to run it for so many steps, learning a rule that's stable over 200 steps, for example, is no easy task. So that makes it rather difficult and also results in poor performance ultimately, which is, of course, not the goal. And the solution to all of these is the Med-NCA training pipeline that we proposed. And let's first have a short look at the architecture, because it's the most interesting, a very interesting part about the NCAs is that the architecture itself is very simple. So in our case, we even simplified it as much as possible. So we only have a single convolution 3D as the input to the model, then a very small dense layer, a batch normalization, a ReLU, and another dense layer, and that's the update to our cell. And this is enough to perform the segmentation. And then we're coming to our actual training pipeline. And this is the important part. When you want to train an NCA, it's much more about the training than the actual architecture of the model. So at first, we had this problem that we have a difficult training because it has to be stable over so many steps to gather global information. So what we do is we first take the input image and we downscale it by a factor, usually by 4. And this allows us to require a lot less steps to gather this global information. And then we run this NCA on this downscaled version, gather the global information. So now we have a small version of the image with global information in each cell. So in the next step, as of course we want to have pixel precise segmentation, we upscale all the global information we have gathered and add the high resolution information to it. But then if we now want to perform the actual segmentation, we're running into the second problem, and that's the high video RAM requirements, because now we're on the full scale image and we would have to keep all the duplications of the model in each cell and also across time. So what we do instead, we use random patches on the second level, and we train the whole architecture end to end on this patch. So we're performing a segmentation loss between the predicted patch and the predicted ground and the original ground truth. And the very interesting part about NCAs, since we have this one cell model size, we're getting the same advantages as the fully convolutional network. So for example, that after training, while we have trained on patches, we can actually do inference on the full scale image. And this actually generalizes very well, which we will see in the results in a second. So our experimental setup will focus on three major parts. First of all, we're going to look a bit at the robustness of the architecture. We want to see the input invariance to see how well it scales to different input sizes. And we will also evaluate the dice accuracy in terms of the model size. And we want to compare it against typical architectures that are used for segmentation. First of all, the classical UNet, also minimal UNet style architectures to see how the UNet deals with a smaller model size. And lastly, also the AutoML pipeline and UNet, as it's still one of the best performance segmentation models and is winning a lot of challenges. And we will compare it on two data sets. First of all, the hippocampus MRI data set from the medical segmentation decathlon, and also the prostate data set. And now if we're looking at the accuracy that we're achieving with the UNet type architectures, we can see, first of all, we're looking at architectures of about a few millions to about tens of millions of parameters. And what we're seeing here, first of all, they of course generally perform quite well. There's a good reason why these architectures have been used for such a long time. But what we also see is that from the general UNet, if we start decreasing the number of parameters, we are seeing also a decrease in segmentation accuracy. And if we're now looking at the NN unit, for example, we can see that having a much more advanced training pipeline, the NN unit does, for example, multiple sets of pre-processing steps. It does augmentations during training and also does some post-processing. And all of this together helps the architecture to be able to perform better segmentation while also being smaller. But we're still talking about millions of parameters, so it's still not very efficient. And then on the other side, we have the NCA type architectures that have 2 to 3 magnitudes less parameters and are performing very well. So for the hippocampus task, we're having similar performance to the NN UNet to about 0.5%. And for the prostate data set, we are a few percent behind. But this is likely because the prostate data set is actually very small. So it only has around 30 patients, and we can also only use 20 for training. So having like augmentations during training can dramatically help the accuracy. And we're not doing such optimizations. We're really only using the model on the data that we have. And just to make it a bit more clear how small the architecture actually is, so I downloaded this picture from the website of the event, and it's about 74 kilobytes, and the M3D-NCA architecture actually fits into the whole image, so it's only 50 kilobytes in size. And if you would compare it and you want to try to do that with a UNet, you would need about 2,956 duplications of this image to fit the whole architecture, just to show how small this actually is. But it's of course not only important the size of the architecture, but also to see that it actually runs on lightweight hardware. And for that, we use the Raspberry Pi 4, which you can see here in my hands. It's a very small PC. And here are the inference times for different image volumes. And you can see that particularly for smaller images, it's quite fast. And even with bigger volumes, we're still having reasonable inference times with up to 2.5 voxels. So next, let's have a look at the input invariance. This is based on the 2D version, but also applies to the 3D version. So here we wanted to see what happens if after training we change the input size of the image. And so basically what we were seeing is that while if we decrease the input size, we can do that for about 30% of the size. And at some point we're seeing some drop in performance, which makes a lot of sense if you think about it, that it's a very different setup. But then if we actually increase the size of the image, we can see that we are very stable and we're only using a few percentages, even if we have twice the number of pixels that the model is going to work on. And this also applies to different types of shapes. So here we were investigating what happens if we cut away parts of the image and leave still the anatomy we're looking for fully in the image. And we can see that for the Med-NCA architecture, there is no issue. We have about almost no drop in performance. And for the UNet, it works for quite some time, but at some point it drops to about by about 12% of accuracy. Surprisingly, for the NN UNet, it actually is trained on such augmentations, but when it becomes too severe, it drops significantly to about 50%. And another interesting thing is if we're now looking at translation invariance, there it makes a lot of sense that the Med-NCA performs very well because it doesn't learn its relation in space, since it's this one cell model size and only works by local communication. So shifting the image around doesn't do any difference. But for the UNet, since it's not particularly trained on dealing with such a scenario, we can see that it's highly overfitted on having the anatomy right in the middle. And we basically fail catastrophically already with a 64 pixel shift of the image. And for the NN UNet, it's again similar as for the shape invariance. We are quite stable for quite some time, but when it becomes too severe, there's a significant drop in performance. In terms of robustness, we're seeing about similar decrease in performance as for the UNet. So for the ghosting, it's slightly better, handling it slightly better. This also might be due to the multi-level architecture. For the NN UNet, the decrease is less because this is actually an augmentation that is trained on. For the anisotropy, there's about no difference for all three architectures. And for the bias field, we're having about a similar decrease. Something that's very interesting I haven't talked about yet for the NCAs is that they are actually activated randomly. So we have this update rule, but it's not applied to each cell and each pixel, but we actually apply it only 50% of the time. And what this means is that if we run the model multiple times on the same input, we always get a slightly different prediction. And the interesting observation we made here is that the more it differs from each run, the more likely it is that the prediction that we're getting is not very accurate. And this we can see here for the hippocampus, where the dice accuracy is about 90%. There's only slight differences around the around the borders of the anatomy. But for the prostate, where the accuracy was a bit worse, we can see that the model is a lot less sure on the borders of the anatomy. And for this, we actually developed quality metric that we can use to make an assumption on how good the prediction is and to detect failure cases. And the NQM score, so the NCA quality metric, is based on the standard deviation between the different segmentations that the model predicts and is divided by the mean of activated segmentation pixels to normalize it. And by this, we can actually make a quite well assumption whether or not a prediction is good or not. And we can see this here, how well this correlates. So we calibrate a linear regression on the training data as well as the training data augmented with noise. And then we evaluate it on the test data overlaid with synthetic spike artifacts and synthetic ghosting artifacts. And something that we're seeing is that if the dice accuracy is still high, we are also seeing a low NQM score, and vice versa. If the NQM score is high, then the dice accuracy is very likely also going to be bad. And we want to look at a few more examples of that now. So first of all, here we have an example. It's all prostate segmentation. And in this case, we have the image on top, the prediction of the NCA in the middle, and then the variance on the bottom. And what we're seeing here is that in both cases, since there's no real domain shift, the model performs quite well. So there's not really much difference in between the different predictions of the architecture of the NCA. And now let's see what happens if we overlay it with noise. So what we can see here is that, first of all, the segmentation accuracy becomes a bit worse with the overlaid noise. And also what we see is that the variance in between the different predictions becomes much bigger. And this also reflects in the NQM score. So we are seeing a drop in the NQM score to about 0.3, or like an increase to around 0.4. And we can see it correlates with the dice accuracy. If we're now looking at the spike artifacts, for example, we can see that here, this first example where the prediction is actually quite bad, we are also having a very high NQM score. And on the other hand, when the prediction is still quite good on the second example, we are also having a low NQM score. And this also applies to ghosting. So in this case, we can see two very strongly augmented images. But in the first example, it's actually failing and it's not really predicting the prostate very well. But in the second example, even though it's very strongly perturbated, we can see that the prediction is still very good, and this also reflects in the NQM. So this just shows that it's actually a viable score that can be used for some failure case detection and might be very useful in some scenarios. And it comes for free if you use, if you do multiple predictions anyways to get the mean and a more accurate prediction, then you basically can run this score in about a few milliseconds. So in conclusion, we have this problem of like a general lack of access to healthcare. And now we have the segmentation method that it can run on any device. It can produce high quality segmentations, and it even has built-in quality control and a few other advantages. So if you're curious about this, definitely have a look at the two publications we made, Med-NCA and 3D-NCA. You can also contact me or my colleagues, Camila Gonzalez or Aniban Mukabade. And there are also here a few videos of first 3 examples are of the 2D variant, and the last one is of the 3D variant, where you can see how this inference process actually looks when segmentation is done. Thanks a lot for listening.